Okay, now we've got a problem. We have a point on a circle of radius 2 meters, and we're moving around the circle at 50 radians per second. That's moving around pretty fast because 50 radians at 2 pi, which is very roughly 6 radians for every revolution, we're going to have over 8 revolutions per second. So we're going around here pretty fast. You wouldn't want to be on that circle. Okay, the question now is, what is the radial acceleration? What do I mean by radial acceleration? This is kind of the thrust of the question. Well, radial acceleration is your centripetal acceleration. Okay, the acceleration along a line that comes out from the center. Okay, a straight line through the center is a radial line. Centripetal acceleration is back toward the center, so it's certainly along the radial line. So centripetal acceleration is radial acceleration. And so the radial acceleration is just v squared over r, which we know to be the centripetal acceleration. If the velocity is 50 radians per second, how many meters per second? How fast are we moving? Because we have to use our speed on the arc to calculate v squared over r, the speed with which we're traveling around on that circle. 50 radians per second multiplied by the 2 meters per radian, because a radian is an arc distance, well, a radian is the angle for which the arc distance equals the radius. So if I multiply how many radians per second times the radius, basically, I get the number, the distance along the arc. And if that's a distance per second, I get if that's a number of radians per second, I get then a distance per second. So this thing's moving at 100 meters per second. Okay, that's like jet speed. It's over 300 miles an hour. No, it isn't. It's about 230 miles an hour. It's still pretty fast. So if your angular acceleration, well, okay, sorry. We complete our calculation of v squared over r then using the 100 meters per second. If we square 100, we get 10,000. Okay, so we get 10,000 meters squared per second squared divided by the radius, which is 2 meters, giving us 5,000 meters per second squared. That's a big acceleration. You would not survive that, not even for a very short time. It's 500 Gs, 10 times what's fatal. Okay, so if your angular acceleration is 3 radians per second squared, what does that tell you about motion around the circle? Well, it tells you that not only are you moving pretty fast on that circle, but you're speeding up, right? Your angular velocity is increasing by 3 radians per second every second. So a second later, you're going to be going 53 radians per second, making this 106 meters per second, and so forth. You're going to be up, closer to 6,000 and 5,000 meters, excuse me, per second squared. So the question now is, what's our acceleration in the direction of motion on that circle? We're not interested in our centripetal acceleration, the acceleration toward the center. We're interested in how fast we're speeding up as we move around that arc. Okay, how fast, if we're driving a car around this thing, not that you drive a car around that small of a circle, but how fast would you be moving around that circle? Then you can't drive a car 230 miles an hour if you get a fast enough car. So, well, the relationship is very straightforward. You got 3 radians per second squared, and every radian corresponds to 2 meters along the arc. So 3 radians per second squared is the same as 6 meters per second squared. So now if we draw the vectors, and I can't draw a 5,000 meter per second squared vector on a diagram along with a 6 meter per second squared vector. It's certainly not on a chalkboard, because this is almost 100 times as long as this one. But, you know, we just do kind of a facsimile. Here's our circle. We're accelerating along here at 6 meters per second squared. We also have a velocity of 100 meters per second, but I didn't indicate that, I just indicated the acceleration. And then we have the resulting radial acceleration, 5,000 meters per second squared. Now this vector should be 100 times as long as this vector. So if I wanted to do these to scale, this vector would have to be a whole lot tinier, but I wanted to indicate the right triangle that gives us the resultant acceleration, because the radial direction is perpendicular to the tangential direction, meaning that this vector is perpendicular to this vector. So when we add the two accelerations to get our resultant acceleration, we just use the Pythagorean theorem. Now if we want to calculate the angle, and well we might, well we just use an arctangent, or whatever, you know, we happen to choose. Okay, the trigonometry is all right triangle trigonometry, so it's very simple.